Have you ever looked at a circuit schematic, spotted that mysterious little triangle, and just felt a sense of dread? Well, you definitely aren't alone. Today, we're demystifying the operational amplifier in this explainer. We're going to completely strip away those confusing textbook formulas and prove that this so-called magical black box is actually just practical, controllable physics. Let's jump right in. So why do we even use these things in the first place? Honestly, because the alternative is chaos. Just look at this. On one side, you have a traditional discrete transistor amplifier. It's noisy, the voltages are drifting everywhere, and it's incredibly unstable. But on the other side, the op-amp, it's giving us this pristine, perfectly stable, and precise waveform. Why does one just descend into total chaos while the other works so beautifully? Well, here is a massive pain point for any engineer who's worked with discrete transistors. If you try to build an amplifier using individual transistors, you are completely at the mercy of parameter drift. Transistors are just highly susceptible to their environment. As the temperature goes up, the current goes up, and these parameters vary wildly, not just because of temperature, but from the actual manufacturing process itself. You can have two transistors with the exact same part number, and they'll behave noticeably differently. It's frustrating. And because of all those environmental variations, the operating point of a transistor, that little red dot right there, it shifts unpredictably. Trying to get exact gain control when you're relying solely on a transistor's internal characteristics, it quickly becomes a nightmare. You end up having to design these crazy complex compensation networks just to keep the whole thing from oscillating. It is a massive headache. Okay, section 1, demystifying the triangle, the golden laws. Let's leave that headache of drifting transistors behind us and look at the op-amp's internal logic, because here is the real secret. It's not that the op-amp is some perfectly precise component on the inside, not at all. It actually possesses this massive, wild internal gain. We're talking hundreds of thousands of times amplification, but this beast is entirely tamed by external precision, by using standard, highly predictable external feedback resistors. All those messy internal variations just fade away and you take the steering wheel. Now, to understand how those external components actually take control, you really only need to know two golden laws of op-amps. Law number 1, practically no current flows into the inputs. We just assume the input impedance is infinitely high. And law number 2, the op-amp will always try to keep its inputs at an exactly equal voltage. When we hook up negative feedback, the op-amp essentially acts like a relentless, self-correcting servo mechanism. If one input is even slightly higher than the other, the op-amp furiously swings its output voltage to feed a signal back to the input until they match perfectly. Let's actually build a real circuit to see this. A simple non-inverting amplifier. Imagine a tiny 10 millivolt signal hitting that non-inverting input. According to our golden laws, the op-amp will do literally anything to make the inverting input match that 10 millivolts. Because our resistors R1 and R2 are exactly equal, they form a divider that cuts the output exactly in half. So to feed 10 millivolts back, the op-amp is forced to push its output up to 20 millivolts. It perfectly doubles the input. And by simply scaling these standard cheap external resistors, we are completely controlling the circuit. Look at the numbers here. If R1 and R2 are both 1K, our gain is 2. But swap R1 out for a 2K resistor. The divider changes, the op-amp immediately adjusts to compensate, and boom, our gain becomes 3. Change it to 4K, the gain is 5. We are entirely in control. This right here proves that op-amp performance is governed by basic, understandable physics, not magic. Because of this perfectly logical equalizing behavior, that standard gain formula that engineers use every single day suddenly becomes incredibly obvious. You don't have to blindly memorize that gain equals 1 plus R1 over R2 anymore. You can literally see it happening right there in the physics of the feedback divider. The math is just a reflection of the op-amp desperately trying to equalize its inputs. Moving on to section 2, math versus physics, the beginner's trap. So here is a harsh reality check for you. Math often ignores hard physical constraints. Let's say you set up a mathematical gain of 100 on a 1 volt signal. Well, the math demands a 10 volt output. perfectly logical on a piece of paper, right? But what if your circuit is being powered by a 9-volt battery? This is impossible. Physics dictates that a 9-volt supply absolutely cannot output 10 volts. No way around it. And honestly, in the real world, it's even more constrained than that. Due to internal voltage drops across the tiny transistors inside the op amp itself, it won't even hit 9 volts. It will typically saturate and clip around 7. 5 volts, it basically hits this invisible ceiling, the supply rail, and it just cannot push any higher. If you hook this up to an oscilloscope, you can see the tragic reality of what happens when math ignores physics. We want that pristine, continuous sine wave on the left, but because the signal tried to exceed the supply rails, the top and bottom are just violently chopped off. Our beautiful sine wave is brutally transformed into this distorted trapezoid on the right. This will absolutely destroy your audio and it'll completely corrupt your sensor data. Which brings us to section 3, the single supply problem. This clipping issue introduces what I think is the ultimate beginner trap, trying to process an alternating current without a dual power supply. Remember, an AC signal swings above and below 0 volts. But if you power your op amp from a single 9-volt battery, it has 0 negative power. It literally doesn't know what to do with anything below 0. So it just completely chops off the entire negative half of the wave. Now a beginner might look at that and think, oh, I'll just shift the signal up and center it at 4, 5 volts. And on paper that sounds pretty smart. But here is the massive catch. The op amp amplifies everything, and that includes your DC offset. If you have a gain of 11, that 5-volt offset gets amplified to nearly 50 volts. Instantly, your output crashes violently into that 5-volt ceiling, leaving you with nothing but a flat, useless line on your scope. It is a dangerously wrong solution. So what is the correct engineering approach? It's using a tiny, carefully calculated DC offset by adding just 0. 15 volts, that small offset amplifies to roughly 6 volts. See the difference? Now, your amplified AC wave is floating safely in the middle of your usable range. It's well above the 0V floor and safely below that 7.5V ceiling. Let's quickly summarize the 3 big physical traps that engineers fall into when they rely entirely on math and forget about the real world. Trap number 1, ignoring supply rails and expecting outputs higher than what the power supply can actually deliver. Trap number 2, not checking if your op amp is actually capable of going rail to rail, which means checking if its output can swing all the way to its power supply voltages without that annoying internal drop. And trap number 3, using incorrect DC biasing when you're trying to amplify AC signals on a single power supply. If you take absolutely nothing else away from this explainer, let it be this core concept right here. An op amp simply changes its output to equalize its inputs. That's it. It is a continuous physical balancing act defined entirely by the external components that you choose to use. It is not magic. It's brilliantly controlled physics. So the next time you look at a schematic and see that mysterious little triangle, what kind of circuit are you going to build with this simple balancing act?